Okay, welcome class. Again, this is for physics 2. There was a question that popped up yesterday when we were doing the magnetic field, basically the circulation of the magnetic field to be more specific. And the question is actually related to the motion in 2D, the displacement in 2D. When we take physics 1, basically we talk about displacement in 1D, then we move to 2-dimension. We don't really do 3D unless we really have to. When it's needed, and a lot of the times basically 3D motion introduces more mathematical complications without introducing a lot of basically new ideas. Sometimes it's needed though. But the point that for the magnetic field, for the circulation of the magnetic field, all we really need is the displacement in 2D. So let me go back into physics, ideas from physics 1, basically. The vector position is defined as the vector. So if I have a Cartesian coordinate system expressed in terms of x and y, in this case on the plane, the position, I can track the position of any object in space using the vector r. So the vector r really is what we define as a vector position. The vector position can change in time, both in magnitude and also in direction. So the magnitude of r is r itself, and the direction is usually expressed with an angle, which I'm going to call theta in here. So basically, this vector r there can be written as in terms of the Cartesian coordinates, x and y. X is going to be definitely equal to r times cosine theta because it's the adjacent, and y is r times sine theta. So the vector r can also be in polar coordinates. First of all, if I call this one the unit vector r hat, then it's simply r, the length of r times the unit vector r hat. In other words, r hat is simply equal to the vector itself divided by its length. So that's true for any vector, actually. It's not just for the position vector. But in Cartesian coordinates, I can still express it as basically x in the I hat direction plus y in the j hat direction, where I hat is the unit vector in this direction and j hat is the unit vector in the y direction. And of course, clearly x is equal to r cosine theta and y is equal to r times sine theta. So from this expression, I can express this r vector itself as being what I just said, basically r cosine of theta plus in the I hat direction plus, of course, r sine theta in the j hat direction. Now note, and this is very important, that both r and theta can be functions of time in the case when the object is moving. So r can be itself, so the length of this vector can be time dependent, and so its direction also, so theta also can be time dependent. So that's basically what we do in physics 1, and we do the special case when the length doesn't change, and that is a circular motion. So the only thing that would be allowed to change then and there is the direction. So that's for the circular motion. Furthermore, actually, we explored the idea of uniform circular motion when the angle does not, changes at constant rates. So those are some of the ideas we do in physics 1. But there is a general behavior in here. So if I'm interested, let's say, for example, in the velocity of the object, and the velocity of the object, the velocity is nothing but the derivative with respect to time of the vector position. Well, I have here I hat and j hat don't change with time, so the only possibility for this vector to change with time is either its length. In other words, a particle can go up and down, basically near or far away from the origin of the axis, or it can basically change direction, or do both. It can do both of them at the same time. So I'm going to take the derivative in here as if it's a mathematical problem, ignoring the physics behind it. So in this case, I have the derivative of r with respect to time, and cosine theta I hat, plus the derivative of r times sine theta times j hat. But I also have theta, which has the potential to change with time, so I have basically to take the derivative the normal way we do it in calculus. So the first part of the derivative is dr over dt times cosine theta I hat plus dr over dt times sine theta j hat. That takes care of the radial change in the radius, basically the magnitude of the radius of the vector position. Now there is also potential for theta to change with time, so I also have to do that too. So plus r, because remember I'm taking this derivative now, plus r times the derivative of cosine theta, that is minus sine theta, times d theta with respect to time. So there is a minus, actually not a plus, I have to take care of in here because of the fact that the derivative of cosine is a minus. So I'm going to put the minus in here. R times d theta with respect to time, and the cosine changes into a sine or a negative sign when you take the derivative I hat, and the derivative here of the cosine, of the sine, is a positive sign, so the sign does not change in that expression, so it's going to stay the positive. R is not impacted by the derivative now because we took care already of it, and I have d theta with respect to time. This is the chain rule times the derivative of sine, which is a cosine of theta j hat. So that is really how, from the vantage point of somebody sitting in a Cartesian coordinate system looking at an object in motion, and that object carries with it its unit vector r hat, except that there is more stuff to it than just the derivative of the magnitude, because there is a potential for the direction to change. Now I can rearrange this expression as follows. dr over dt is equal to dr over dt in magnitude times this vector in here, cosine theta I hat plus sine theta j hat, that's this one, and plus another term that involves that combination of r times d theta over dt. D theta over dt is omega, actually. That's the angular velocity. So, but we're going to leave it as is, so don't worry about that right now. So plus r d theta over dt times, I am left with a minus sine theta I hat plus cosine theta j hat. Now cosine theta I hat plus sine theta I hat is nothing but actually r over r. So r vector over r is equal to, remember r itself is just r times this quantity. This is from the top in here. This is where r cosine theta I hat plus r sine theta j hat. If I divide the entire expression by r, I'm left with cosine theta I hat plus sine theta I hat, which is actually r hat. So r hat is actually simply cosine theta I hat plus sine theta j hat. So that takes care of this vector in here. I'm looking at this vector, which I'm going to call from get-go theta hat, and I will tell you exactly why I'm calling it theta hat. I'm going to call this theta hat as being equal to minus sine theta I hat plus cosine theta j hat. First of all, its magnitude is 1 too. Actually, you can check the magnitude of r hat to be 1 just from the trig identity, because the square root of the x component squared plus the y component squared is the square root of cosine squared plus sine squared, and that is 1. The same thing is true actually for I hat too. If you take its magnitude, the magnitude of this vector, theta hat, is the square root of minus sine theta squared plus cosine theta squared under the square root, the x component squared plus the y component squared. Minus squared is going to be positive. Sine theta squared is sine theta squared plus cosine theta squared. So this vector, actually, the length of which is 1, 2. So this is a unit vector. Furthermore, this vector is actually perpendicular to the vector r hat. And let's check that. If you do the dot product of these two vectors, r hat dotted with theta hat, you will find that the x component for this vector is minus, the first vector is cosine theta, and the second vector is minus sine theta, plus sine theta times cosine theta, that is 0. And that is how two vectors are going to be perpendicular. You just check the identity in here, it should be 0. X times the x components, cos times sin with a negative sign, and then here you have sin times cos with a positive sign, and they do cancel out. So these two vectors are perpendicular, not only perpendicular, but perpendicular in such a way that actually R makes an angle of a positive 90 degrees, because you can say that, hey, R could be positive 90 degrees or negative 90 degrees. So if this was R hat, then, in other words, theta hat could be here, and theta hat could be also here, because that's basically what the condition of two vectors be perpendicular. So theta hat could be up or down, but the correct answer is this one, and you can actually check it by doing the cross product very easily, and you can find that this cross product in the Cartesian coordinate system of r hat theta hat, where r hat and both theta hat have no z components, as you can clearly see there is no k hat in here, so both of them have zero components in that direction. So this is 0, this is 0. Furthermore, r hat has components which are cosine theta and sine theta. So the components of r hat are cosine theta, sine theta, as you can clearly see from this expression, cosine theta and sine theta. Whereas the components of theta hat are minus sine theta and cosine theta. Minus sine theta, cosine theta. And if you do the cross product, the x component cancels, because 0 times sine minus 0 times cosine is 0. The j component also cancel, because cosine times 0 and 0 times minus sine is 0. And the only component that's going to survive, of course, is going to be in the k hat direction, and it's cosine times cosine, that's cosine squared, minus times minus, that becomes a positive, because the expression has a minus in it, and this component is minus, so it's going to be a positive sine times sine, sine squared. So at the end, it's going to be cosine squared plus sine squared times k hat, which is k hat. So these two vectors, they curve in this direction. That means the sign between them is equal to positive 90 degrees, because this product, I can express it also in terms of its just numerical value as being 1, which is the length of r hat, times 1, the length of theta hat, both of them are unit vectors, you can clearly see it from above, and times the sine of the angle between them, sine of the angle between r hat and theta hat, and that is equal to, well, this is 1, because the vector k hat has a magnitude of 1. So at the end, this angle must be positive 90 degrees. That's the 1. That's the angle that makes the cross product, the dot product, to be 0. They are perpendicular. Furthermore, the cross product to be exactly positive 1, and that is a positive 90 degrees. In other words, these two, they go into one another. They form a right angle triangle. A rectangular coordinate system similar to I hat, j hat, k hat. This they form r hat, theta hat, and k hat. So that's actually another Cartesian coordinate system in 3D. Now you can easily also find the fact that this is theta is 90 degrees by just checking the trig identity that basically you guys know from before, that cosine of theta plus pi over 2 cos, which is 0, cosine of 90 degrees is 0, minus sin, and sin of pi over 2 is 1, so this is minus sine theta. And also, sine of theta plus pi over 2 is sine times cos, and cos of pi over 2 is 0, plus cos times sin, and sin of pi over 2 is 1. So at the end, this will end up being cosine of theta. And this too, minus sine theta and cosine theta, are exactly the coordinates of theta hat. Minus sine theta is its x coordinate, and cosine theta is its y coordinate. And they are cosine and sine, except that they are shifted with a positive 90 degrees. In other words, this vector theta hat is truly a vector that is a rotation of the vector r hat itself by an angle of 90 degrees. So r hat is in the direction with which this object can rotate, so therefore the actual vector dr over dt, that is where we started from, is equal to dr over dt in the r hat direction, now plus r times d theta over dt and a perpendicular vector to it. So that's basically how this looks like. So therefore, if I go back into my initial vector, the way this vector can grow in two ways. It can grow in the radial direction by by an amount dr, and during an amount dt, that's the rate at which it's growing, or it's going to grow in this direction, in the theta hat direction, which is perpendicular to that direction, with an amount that is actually r times d theta, as you can clearly see from this expression. Because if I am only interested in the increments of this vector, I'm not really looking at their rates with respect to time. So dr as a vector, this is a vector, I'm sorry, dr as a vector is dr in magnitude, r hat, plus r d theta in the theta hat direction, in the azimuthal direction. So that was the result we were talking about yesterday when we were doing the magnetic field and the circulation of the magnetic field, and it was this component at the end that was of interest to us, and this component actually canceled when you do the circulation of the magnetic field, because the magnetic field goes in only in the azimuthal direction, and when you do the dot product of the displacement, which is in the azimuthal direction, which is in general, this is the displacement times the vector, that is actually in the theta hat direction only, so the dot product will just yield this one. In other words, when we were doing the magnetic field, at some point the magnetic field is only azimuthal. It has some value in here which is not important, but the point being in here is that it's only in the theta hat direction. Obviously, when you do b times the displacement, this component of the two will give you zero contributions, because these two vectors are perpendicular to one another, and the only thing that survives basically the calculation from the dot product when you're calculating circulation of vectors is this two terms. So that clarifies that. I'm just going to show you a quick animation I did with GeoGebra basically for displacement in general. This is a particle that has a little bit complicated actually motion. It's actually non-linear, and it's non-linear because of this term in here, t to the power 4 and the cosine itself, and that's part of the argument of its x position and its y position, and the whole thing basically goes hayward. I mean, initially it starts smooth, but then actually, so the point in here is that both r, the position vector of this particle, and also its angle are changing with time. And because of that term, basically the nonlinear term, the behavior starts to become a little bit kind of chaotic a little bit, although it's controlled in this situation because we know the value, so it's not really random. But the point being in here is that the r is changing both in magnitude and direction, and this is the general motion of the particle. This is not a uniform circular motion. This is not even a circular motion. So this particle is moving basically in what appears to be a random, and it's on the plane actually, and both its magnitude, the magnitude of its vector position r, and also its direction are changing with time, and that is exactly my point in here. So you can have both of them change in the same time and move. When we were calculating the circulation of the magnetic field around any path that this particle describes, at the end of the day, that doesn't matter. It's going to be just the direction of and the azimuthal direction that matters only, not anything else. Okay, I hope this clarifies that. I'm going to post this stuff on Canvas so that you guys will have a chance to basically go through these things if you have any doubt about it. But at the end, when you calculate the circulation of the magnetic field, it should be the same thing that we calculated yesterday. Thank you.